All right, so we're going to finish up talking about gravitation with talking about gravitational fields. So I encourage you to go watch this video. You can find it anywhere on YouTube, the feather and hammer drop on the moon. So on one of the Apollo moon missions, an astronaut dropped a hammer and a feather in a complete vacuum. So that means there was no air resistance. And they dropped them at the same time. So I want you to pause this video, go find the other one, either on my slides or on YouTube, and let's see what happens. Just watch. It's very short. Okay, so you've watched the video, and in the video, the hammer and the feather dropped onto the surface of the moon at the same time. So we find that no matter what the object is, no matter how massive it is or small it is, it should fall at the same rate. All objects on the surface of the planet Earth or on the moon, they're all observed to fall at the same rate, the same free fall acceleration. It doesn't matter if it's an elephant or a feather or a hammer or a monkey, it's all going to fall at the same rate. So my question to you is G, or the acceleration due to gravity, affected by both the mass of the moon and the object, or just by the moon? To help explain how two bodies that are not in contact can exert a force on one another, so gravitational, magnetic, electrostatic, we use this concept called fields. Fields are spheres of influence. They are invisible and intangible. They determine how strong a force is at a certain distance. And we can think of fields kind of like a campfire. So think of a campfire as having a heat field. The closer we get to the fire, the stronger the field becomes. Likewise, the larger the fire is, the further away we will notice its field. So you get close to a fire, you get all warm and toasty, and if you're standing further back, you're not going to feel that warmth as much. If you have an itty bitty tiny fire, it's not going to feel as warm as a great big bonfire. So you could think of that heat field around a fire. So we have gravitational fields, and we call them by the variable little g, and they're given by these two equations. The first one you've seen, it's just the rearranged form of Newton's second law. So it's little g is equal to the force due to gravity over the mass, or F equals mg. And the other formula you haven't seen, we can solve it using Newton's second law and Newton's law, universal law of gravitation. I won't go into that right now, but if you want to see a derivation, I believe there's one in your textbook. So the other equation is G is equal to big G times m over r squared. So big G, again, is your universal gravitational constant, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Big M is the mass of the planet or moon that you may be on. And little r is the distance between the distance from the center of mass of that large object. So in the case of standing on the surface of Earth, it's the radius of the Earth. Our units for gravitational fields can be either meters per second squared or newtons per kilogram. So both are acceptable. Newtons per kilogram is fine too. When we're doing accelerations, typically we want to do meters per second squared. When we're talking about fields, newtons per kilogram is nice, but meters per second squared is totally acceptable. So, revisiting the hammer and the feather. The more massive object, which is the Earth in this case, or the moon in the case of the Apollo experiment, is the only thing affecting the acceleration of the hammer and the feather. So the planet or the moon is the only thing that's going to affect that acceleration when we have such tiny objects compared to the Earth. Both masses will affect the force between them, but only the greater mass affects the acceleration when one of the masses is very small compared to the other. So here's an example. The Earth is not actually a perfect sphere. Just like a spinning basketball, it is an oblate spheroid. So that's a nice way of saying that it's kind of bulgy in the middle. So I want you to try to calculate the gravitational field, or the acceleration due to gravity, at the North Pole, where the radius of the Earth is 6.37 times 10 to the 6 meters, and at the equator, where the radius of the Earth is 6.386 times 10 to the 6 meters. You're going to use your newfound equation, G equals gm over r squared. So give that a try on your own, and you should find something that's pretty close to our accepted acceleration due to gravity, which is more of an average that we use for the surface, 9.81 times 10, or sorry, 9.81 meters per second squared. So you'll find that one of them is smaller and one of them is a little bigger than that, but they should be fairly close. Here's another one that you can try. The moon is 385,000 kilometers away from Earth's surface. What is the gravitational field strength at this distance? Be sure to convert 385,000 kilometers to meters before you tackle this problem. And you're also going to want to add that value to the radius of the Earth, because we're talking about center of mass here. So use your newfound equations to calculate this. And then I encourage you, when you're done, to check out this video. It's Brian Cox from the BBC, and he's visiting the world's largest vacuum chamber, and he drops a feather, and I think it's an ostrich feather, and a bowling ball in this giant vacuum chamber, and he's trying to show that they should fall at the same rate and hit at the same time in the absence of air resistance. So I recommend you go and find that video and watch it. Again, it's linked in my slides in Google Classroom, or you can just Google it or type it into YouTube. So that's all I have for you with gravitational field. And next time we're going to talk about circular motion.